Hi there, welcome to another video from HEGARTYMATHS, a Core 4 Maths A-Level video. It's the 9th and final video on vectors, and we're again talking about the dot or scalar product, but this time with vector equations of lines. As I always say, this is for the Edexcel syllabus. We now have covered off everything here, but we're just going to talk about the scalar product in the context of equations of lines, and then I'm going to do exam style questions. Let's just extend what we did in the last video to vector equations of lines. You will remember that if I had two vectors A and B, I could work out the angle between them by using cos theta is A dot B over the modulus of A multiplied by the modulus of B. Now suppose we have two, not vectors as such, but lines. Let's say we have two lines, and this is line, a vector equation of line. This is line R1, and it's equal to vector A1 plus, let's say, T lots of vector B1. Okay, remember the definition of a vector equation of line: a point on the line plus some lots of the direction of the line. And let's say we had another vector R2, and that was the position vector A2 plus S lots of the direction of the line B2. Okay, and we wanted to find the angle between the two lines. What would we do? Well, to do this, all we've got to think about really is we don't really care about the position point on the line at all. All we care about is the direction the line is going. Now, if you remember your vector equation of a line, this part here is the direction. So if we wanted to work out the angle, we would use cos theta, and we would do in this case B1 dot B2 all over the modulus of B1 multiplied by the modulus of B2. We would just use the directions for that. Okay, that's all we would do. Now, what's probably easiest in the exam, I'm just going to write this with different notations. Suppose here this was line R1 here, and the vector equation of line R1, and this one here was R2. What might be easiest is to call maybe the position vector in R1 P plus let's say S lots of vector A. The position vector of one of the lines is A, and R2 we might call a position vector to start with Q plus T lots of B, the direction vector for line 2. So we would call A the direction part of line 1, we would call B the direction part of line 2, and again we would use the formula cos theta is A dot B over the modulus of A, the modulus of B. It might just be easier to keep our notation, so that's why I rewrote that there. So that's all we've got to do. To deal with this in terms of vector equations of lines, just pick out the direction component of each line and do the same process as we've done before. So let's have a go at an example. Find to one decimal place the acute angle between the lines with vector equations as follows. So this line here, we could write that as 2, 1, 1 plus T lots of 3, negative A, negative 1, the first one. The second one we could write as 7, 4, 1 plus S lots of 2, 2, 3. Now the direction components are these parts. So we just have to identify that, and we're going to work out the angle between these. So we're going to let A be equal to 3, negative A, negative 1. We're going to let B be equal to 2, 2, 3. We're going to write our formula down that we're going to use. Cos theta is equal to A dot B over the modulus of A, the modulus of B, and we're going to go on and work out each component. Right, so A dot B first of all. A dot B, that's going to be equal to 3, negative A, negative 1, dotted with 2, 2, 3. So we're going to get ourselves 3 multiplied by 2 plus negative 8 multiplied by 2 plus negative 1 multiplied by 3. If we do that, let's just scroll down the page a tiny bit here. So we're going to get ourselves 6, subtract 16, subtract 3, and that's obviously going to be equal to negative 13. So A dot B is negative 13. If we work out the modulus of a, well, that's clearly going to be the square root of 3 squared plus negative 8 squared plus negative 1 squared. And if we work that out on our calculator, we get the square root of 74. If we work out the modulus of b, well, that's going to be the square root of 2 squared plus 2 squared plus 3 squared. And we're going to get ourselves the square root of 17 there. So therefore, what we can write is that cos theta must be equal to negative 13 over the square root of 74 multiplied by the square root of 17. So when you type that in your calculator and work out the inverse cos, you get that theta is equal to 111.5 degrees. Now, looking up at the question, it asks clearly for the acute angle between the lines. So we've got two lines here going as such, and we know that it's 115. Therefore, you know, the acute angle between the lines is 180. Take away that if you want to work out the acute one. So it's therefore 68.5. So theta equals 68.5 degrees to 1 dp. Okay, and we're done in that regard. Now it's time to try a few exam questions. These exam questions will use all of the knowledge of the previous 8 or 9 videos to in the exam style questions. So you may want to pause the video, have a go, and if you're stuck, you can watch me go through it and see the style of question. Okay, so here's an exam style question. We want to find the point of intersection of the line through the points 2, 0, 1 and negative 1, 3, 4, and the line through the points negative 1, 3, 0 and 4, negative 2, 5, and calculate the angle between the lines. So let's just draw a picture to see what's going on. We've got two lines here, let's say. On one of the lines, you know there is the point the coordinate 2, 0, 1. So this point has position vector relative to the origin 2, 0, 1. And you've got another one up here that is on the line, so negative 1, 3, 4, you know, is on the line. You've got another line here that has a point on the line which is negative 1, 3, 0. So it's got a position vector to there, and you've got another point on the line which is 4, negative 2, 5. You don't know the directions of the line, you know the lines intersect. So the first thing we should do is work out the direction of that line and the direction of that line, surely. And this we might call line 1, and this we might call line 2. So let's do line 1, the direction. Okay, well, the direction would be that position vector take away that position vector, because it's telling you, it would tell you that vector there. So it would be equal to negative 1 subtract 2, 3 subtract 0, and 4 subtract 1, which would be negative 3, 3, and 3. That's the direction there. So the direction of the line is any multiple of that. Let's simplify that. A nice direction of the line, if I divided everything by 3, would be negative 1, 1, 1. Just think for a second why I can do that. I'm just cared about the direction of the line, not a point on the line. I couldn't do that with a point on the line, but that direction is the same as that, apart from that's 3 times bigger. And we're going to use r equals a plus t times the direction, so it doesn't matter that I've simplified this direction component. So there's the direction of that line. So I could therefore write that r is going to be equal to 2, 0, 1 plus, let's say, t lots of negative 1, 1, 1, which could combine up nicely to 2 subtract t, t, and 1 plus t, let's say. Okay? Okay, let's do the same with line 2. This is line 2 here. Let's get the direction. Well, let's just do that, take away that. So I would do 4 subtract negative 1, negative 2 subtract 3, and 5 subtract 0. I'd get myself 5, negative 5, and 5. I'd simplify that. I should have just written simplify. It just makes it easier when I'm dealing with directions to have the simplest one. 1, negative 1, and 1. So therefore I could write the equation of this line, r is the point on the line, negative 1, 3, 0, plus t lots of the direction of the line, 1, negative 1, 1. And combining those, I would get negative 1 plus t. 3, let's not use t, sorry, my fault here. Let's use s, a different letter, just so it doesn't confuse. That's s, so negative 1 plus s, 3, subtract s, and s. Okay, so if I want to work out where the lines intersect, I make these two equations the same. So what I could solve here, I could therefore solve 2 subtract t, t and 1 plus t. That vector equation must be equal to this vector equation. And so the x components must be the same, the y components must be the same, etc. So from this I can deduce that 2 subtract t must be negative 1 plus s. I could deduce that t must be 3 subtract s, and I could deduce that 1 plus t is equal to s. Now, it just so happens if you play around with equation 1 and 2, you don't get an answer. They're the same equation, just rewritten. If you look at them carefully, you can see they're the same equation, just in a different format. These two are different equations, so I'm going to use these two. T is equal to 3 minus s, so therefore, if I call that equation 1 and that equation 2, if I put 1 in 2, I would get that 1 plus 3 subtract s is equal to s. Add s to both sides, I'd get 4 is equal to 2s. So s is equal to 2. Using s is 2, I get t is 1. Now it wants the coordinates of intersection, so therefore the intersection, well, I could either put s is 2 in that or t is 1 in that. I should put them in both and check they're the same so I haven't made a mistake. If I put s is 2 in that, I get 1, 1, 2. If I put t is 1 in that, I get 1, 1, 2. So there's my intersection. And the next part is the acute angle between the lines. Well, I know that cos theta is going to be a dot b over mod a mod b, where a and b are the directions of the line. A must be minus 1, negative 1, 1, 1, and b is the direction of the second line, which is 1, negative 1, 1. 1, negative 1, 1. So I can work this out here. Cos theta would be a dot b, which would turn out to be equal to negative 1 over the modulus of this one, which would be root 3, and the modulus of that one would be root 3, so it would be root 3 times root 3, which is 3 obviously. So cos theta is going to be equal to negative a third. So theta, if I type in my calculator, the inverse cos of negative a third, and I get myself 109.5 degrees. But I want, if I look up here, I want the acute angle between the two. So the acute angle must be that, take away 180. So the acute one must be equal to 70.5 degrees. And we're done. And here's a second exam style question. This actually came up from last year's paper. I've reduced it in small here. I'm going to try and do it beside it so we can just see our work as we go along. With respect to fixed origin, you've got lines 1 and lines 2, where mu and lambda are scale parameters. Given that L1 and L2 meet, find the position vector of their points of intersection. Just before I do the work in here, some extra work in. For line 1, I might write the vector equation of the line as 9, 13, negative 3 plus mu lots of 1, 4, negative 2, and I might combine that in the form 9 plus lambda, 13 plus 4 lambda, and negative 3 subtract 2 lambda. It's just easier like that. And I'll do the same with the other one with line 2. I might write that instead as 2, negative 1, 1 plus mu lots of 2, 1, 1, and I might combine that, so it's 2 plus 2 mu minus 1 plus mu and 1 plus mu. Okay, now L1 and L2 meet, find the position vector of their intersection. If they meet, we can say for part A that clearly 9 plus lambda, 13 plus 4 lambda and negative 3 subtract 2 lambda must be equal to 2 plus 2 mu, negative 1 plus mu, and 1 plus mu. Okay, so we could definitely say that. Now, therefore, for them to be equal, all three components can be equal. I can make two of them equal, solve for mu and lambda, and then check that each of them are equal. So, what I can say from the first one, from the top line, I can say that 9 plus lambda must be equal to 2 plus 2 mu, and subtracting 9 off both sides, lambda must be equal to, if that would be negative 7 plus 2 mu, which I might write as 2 mu subtract 7. Okay, from 1. Okay, and then from 2, I might write that 13 plus 4 lambda is equal to negative 1 plus mu. And I could substitute in lambda in here. I could therefore, I could write 13 plus 4 from this equation, 2 mu subtract 7 is equal to negative 1 plus mu. Tidying it up, 13 plus 8 mu subtract 28 is equal to negative 1 plus mu. I could combine these, so 13 subtract 28 is negative 15, so 8 mu subtract 15 is equal to negative 1 plus mu. Take away mu off both sides, 7 mu, add 15 to both sides would be 14, so mu would be 2. If mu was 2, lambda up here would be 2 times 2, which is 4, take away 7, which is negative 3. Now, if that was the case, let's check it does work. The intersection point, therefore, intersection, well, it would be what happens if I put lambda as negative 3 in here. 9 subtract 3 would be 6. 13 plus 4 times negative 3 would be 13, take away 12, which would be 1. And negative 3 subtract 2 times negative 3. Well, negative 2 times negative 3 is 6, so negative 3 plus 6 would be 3. Let's check it actually works the other side in case I've made a mistake. If mu was 2, 2 plus 2 times 2 would be 6. Negative 1 plus 2 would be 1. And 1 plus 2 would be 3. So I know that's the point of intersection, and I'm happy with that. Okay, so that's part A done for 5 marks. Let's do part B. I'm going to rub this out and do part B. Now, part B asks us to find the acute angle, so let's make sure we highlight the word acute, between line 1 and line 2. Give your answer to 1 decimal place. So we're dealing with the position vector, the direction vectors, that's what we care about. So we're going to write down our formula that we're going to use. We're going to say that cos theta is going to be equal to A dot B over the modulus of A multiplied by the modulus of B. And we're going to let A be the direction part of line 1. So the direction part is 1, 4, negative 2. And we're going to let B equal the direction part of line 2, which is 2, 1, 1. So, A dot B, let's work out each part. A dot B is going to be 1, 4, negative 2, dotted with 2, 1, 1. And we're going to get ourselves for that 1 times 2 plus 4 times 1 plus negative 2 times 1. If you work that out there, you're going to get yourself 4. So A dot B is 4. The modulus of A is going to be the square root of 1 squared plus 4 squared plus negative 2 squared. And you're going to get yourself the square root of 21 for that. For the modulus of B, we're going to get the square root of 2 squared plus 1 squared plus 1 squared. And you're going to get yourself the square root of 6 there. So therefore, cos theta is going to be equal to 4 divided by the square root of 21, the square root of 6. And if you apply inverse cos to that, you're going to get yourself that theta, the angle between them, is 69.1 degrees to 1 decimal place. And you've done part B for 3 marks. Okay, next part, part C. It says, given that the point A has position vector as follows, and that the point P lies on the line L1 such that AP is perpendicular to line 1, find the exact coordinates of P. So this seems quite complicated now. Let's draw line 1 out again. Let's just try and draw a picture. Line 1 is this here. So a point on the line that we know is 9, 13, negative 3. Okay, and we know the direction the line's going in. The direction the line's going is 1, 4, negative 2. Okay, actually I'll just write this as a position vector for now. I'll write this as a rather than a coordinate. The position vector to get here from the origin, which might be origin there, is going to be 9, 13, negative 3. That vector there that gets you there to there is going to be that. There's a direction vector, that's line L1. We're told that point A has position and lies, point A has position vectors following, and point B lies on the line such that AP is perpendicular to line 1. So let's have a point on the line. Here's a point on the line, any point. Okay, and A is perpendicular to line 1. So AP is perpendicular. So A must be some point over here. And AP is perpendicular to the line, the direction the line's going in. So this here must be A. A is some point not on the line, but AP is perpendicular to the direction the line's going in. It asks you to find the exact coordinates of P. Well, we're told the position vector of A is 4, 16, negative 3. So this the vector from the origin to here is as follows, 4, 16, negative 3. So, the one fact we can use, we know that the direction of this line and the direction of this line must dot to be 0. Okay, so we have to work out how do we work out the vector A to P. Now we know P is a point on the line, so P being a point on the line, it's any point on the line is of the form 9 plus lambda, 13 plus 4 lambda, and negative 3 subtract 2 lambda. For some lambda, that's true for P. So therefore, what is the vector A to P? Well, A to P would be this vector, take away this vector. Okay, if you subtract them, so it would be the vector from A to P would be 9 plus lambda, take away the 4. It would be 13 plus 4 lambda, take away the 16. And it would be negative 3, subtract 2 lambda, subtract the negative 3. Okay, and if we work that out, it would be equal to 5 plus lambda, 4 lambda, subtract 3, and in the last case here, it would be equal to negative 2 lambda. So that's the direction of AP. Now we know for sure that AP and the direction of the original line are perpendicular. So therefore, the direction of the original line is this, the direction of AP is that. If we dot these two together, these vectors, then we will get 0. So 1, 4, negative 2 dotted with 5 plus lambda, 4 lambda subtract 3 and negative 2 lambda must be 0. So we can work this out. So 1 times this, we'd get 5 plus lambda plus 4 times 4 lambda subtract 3 plus negative 2 times negative 2 lambda must be 0. Times this out, we get 5 plus lambda plus 16 lambda minus 12, and we get here plus 4 lambda equals 0. How many lambdas have I got? 1, 16 and 4, so that's 21 lambda, and we've got 5 take away 12, which would be equal to negative 7. So 21 lambda subtract 7 is 0. So 21 lambda is equal to 7. So lambda must be 7 divided by 21, which is 1/3. Okay, so we've got lambda as a third. We want the coordinates of P. Well, P, we've said, is the following. 9 plus lambda, 13 plus 4 lambda, and this here. So we know that P is therefore going to be equal to 9 and a third, 13 and 4 times a third, so that's going to be 14 and a third, and negative 3, subtract 2 times a third, and we're going to get ourselves negative 3 and 2/3. So P is 9 and a third, 14 and a third, and negative 3 and 2/3. And that's it for this video. Thank you for watching. Do make sure you read chapter 5, page 81, and you complete the exercise 5J, all of it, and start through the miscellaneous exercise questions 1, 4, 5, 8, 9, 10, and 14. Thank you for watching.